Have you ever wondered how we see the world and process information? Have you also pondered how we can give vision and eyes to our robots? In today's episode, we will talk about vision sensors or imaging sensors, and we will demystify how they come to be and how you can use them to give your robots the superpower of vision. Remember from the last time, we talked about the robot definition as perception, then planning, and control. Today's class, we will be talking about perception. And we also talked about what a sensor is, and which is like how we perceive the world. And we looked at a bunch of the types of sensors which are based on how humans perceive the world. Like I alluded to before, we will talk about today's sensor, which is vision-based sensors. Vision or eyes are the most ubiquitous robotic sensor. This is commonly called as a camera or an imaging sensor because it has a wonderful variety of properties. I want you to pause this video and ponder upon why cameras are so popular. Why do we use them? Why do we see so many cameras around us, and why we capture so many images and share it with our loved ones? The first is cameras are cheap. Because of our cell phone revolution, we have produced cameras which cost just a few cents. So we can easily put multiple cameras on our robots and easily utilize this information to do wonderful things, as we will see in multiple sets of videos in this series. The camera gives us dense information. Dense here meaning that the angular resolution of the sensor is actually very, very good. You can get up to sub-angular degree of resolution with the sensor, right? Remember, we talk about like 12 megapixels, 24 megapixels, 108 megapixels on our camera. And that's a lot of information in a small, tiny package, right? And it mimics one of our own senses, which means that it's intuitive for us to understand what is going on. When we look at an image, we instantly know what the feeling of that image is. We instantly know what is going on in that image. And we want to give our robots these superpowers. And these cameras are multifunctional in the sense that you can use the same camera or the image to do a multitude of tasks, like knowing where it is in the world, knowing what is there in front of it, knowing if there is an obstacle, knowing if there is something safe to do, and so on and so forth. And this is like a tweet from 2021 from Elon Musk, wherein they said, like, in the Tesla driving cars, computer vision or like cameras were so good that they actually turned off the radars and they were not using radars anymore after that. And his point was that humans drive with eyes and biological neural networks, and it makes sense that Tesla cars do the same thing, and so on. However, as we go along in the series, we will start to unravel and demystify more of why cameras are spectacular and where cameras actually fall short. Right? And then you can be the best judge of if this was a very wise decision or if this was not, or if we should be thinking about other sensors which we don't have, right? And we will see. Here's a small story. One of my friends was driving in a self-driving car, and he was testing out the early version of their self-driving suit, and he was driving in a hilly road. He's in the shiny yellow car, which is the self-driving car they have built, and he sees he does not know that there is a crashed car on the other side of the hill, right? And while he is driving, he's on the other side of the hill, and of course he does not see this crashed car. He gets a big alert on his dashboard saying that, hey, there is a potential collision detected and there is something in front of you. And my friend, being startled, he's like, I don't know what is going on. Why is this happening? So I want you to pause the video and think for a second what could have happened and why he got this alert. So what had happened is that this car was equipped with not just cameras but also radar sensors, like we saw in the previous case, which was turned off by Tesla. And the radar had basically seen through the mountain. So radar sensors have a penetration power which can go through objects, as we will see later on. But cameras cannot see through walls or see through mountains, like we know, right? We as human beings don't have the superpower like Superman, wherein we can have X-ray vision to see through stuff. So, but radars could actually do that. So this might be super important for us to consider if we are considering driving in like really precarious situations, like a lot of mountain roads, or like through dense fog or through dense rain and dense snow and stuff, where vision sensors actually struggle quite a bit. So, but in other cases, most of the scenarios, vision sensors are spectacular and they're wonderful, and we rely on them for almost every single thing in our everyday life. So let's dwell more into how vision sensors work and what are the parameters which sort of affect their performance. Vision sensors in like robotics are also called imaging sensors because they essentially capture an image. When we look at a camera, you might think that the entire camera is called a vision sensor, but that's not the truth. It's just this physical sensor itself which captures light, right? And if you have like a Raspberry Pi HD camera, which is shown on the left here, if you open it up, you see this little gray square behind the blue colored filter, and that's basically the imaging sensor. And if you have like a DSLR or a mirrorless camera, as we will talk about later, if you like take out the lens, you will see the sensor itself. On your smartphones, most of the times you would not see it, but again, like this is the actual sensor itself, right? To make life very simple, let's forget about color for a second and let's just talk about grayscale imaging. This is basically what you would call black and white images in the 1940s and 50s. But the technical term for it is grayscale imaging because it has all the light values going from black to pure white. Right? Each unit or subunit of this grayscale imager / camera is called a pixel, or the picture element unit of light. Right? And each of these pixels basically measures a number of photons per some unit time. So here number of photons is basically the amount of light intensity that is falling on that particular pixel, and the amount of time is basically how long you are actually capturing this image for, which has a nice little better name, as we will come and see later on in the next few slides. Cool. And so like I said, again, like each of these picture elements is called a pixel, which you would have heard before, but now you know why it is called a pixel. So generally there are two very common kinds of cameras. The first one is a DSLR, or digital semi-lens reflex. The idea is that you have a physical mirror as shown in the blue here on the left side, which is basically going to flip up out of the way to actually like let light into the image sensor, which is shown in black. And as you want to capture the light, you press the shutter button, and basically the mirror flips up and all the light from the world falls on the image sensor for some small unit of time, let's say like a few hundred milliseconds or like a few seconds if it's a very dark scene, right? And then you put the mirror back in its position, the image stops, it completes capturing, and you actually finally get the image. So DSLRs are great because you actually rely on your own eyes and you can actually see what you're going to be getting in the scene, and you see that through the pentamirror prism as shown on the top there. This is like the olden school technology where the cameras are pretty bulky because the physical mirror is pretty big and the size of the mirror scales along with the size of the sensor. The cameras could become pretty bulky and heavy, right? And this physical mirror again uses mechanical shutter to physically move around. So that also limits how fast you can take images. Awesome. So in the newer day era, in today's day and era, if you go out and try to buy a camera which you can change lenses, you will probably end up buying something called a mirrorless camera. What it does is it simplifies the DSLR. It keeps the best part of the DSLR, which is changeable lenses, but it also lets you see through the viewfinder what the image would be captured through an electronic shutter. Basically the idea is that you don't have a physical mirror anymore, so you have like a translucent kind of screen where light actually falls on this translucent screen called the shutter unit, and it basically processes or pre-processes the image, and that is thrown into a viewfinder which is actually a digital screen, and the image sensor does exactly the same thing as we were doing before. The first versions of mirrorless cameras were not that great, because this would mean that you were losing quite a bit of light on the shutter unit, right? Unlike the DSLR case where the mirror would flip up to give you the full light intensity of the world, this would actually bad. But with amazing digital processing, we can now actually get much higher image quality with mirrorless cameras than DSLRs, and they have better autofocus capabilities. They have better features because of AI and stuff like that, which can pre-process the data on the shutter unit, and the automatic settings and everything is just much better. So most people again would buy mirrorless cameras, and mirrorless cameras are slightly more expensive than DSLRs. Again, they're awesome technology to buy from. So just to quickly recap, a camera has a bunch of things. You have a lens, which is basically the thing which focuses light to capture the image. You have the aperture, which we will talk about in a few seconds. You have the mirror in the DSLR, which would flip up, and in the mirrorless setup, you will have a assembly there for the shutter mechanism, and you have the image sensor, you have the viewfinder screen, you have the shutter release button, the pentaprism mirror in the case of DSLR where you would see the viewfinder. In the case of a mirrorless camera, it would be a screen, and you would basically see the eyepiece window. Next, let's start talking about a few important parameters of a camera. If you want to go and buy a camera, you need to know these things, and it's super important for you to understand these, because you're going to use these things to buy a camera to put it on a robot. And of course, it depends on the task you're trying to do with that robot, right? The first one is called the focal length, which is basically like how much the bending power of the light of the lens is. If you can also think of it as like how much zoom it is into the world, or how wide of a scene you actually see. And the way you would get the focal length of a lens is basically you take something really far away, like we call it at infinity for mathematical terms, like the sun, and you would basically move the lens back and forth, where you would actually get the perfectly sharp image of the sun on your image sensor, right? Please do not do this with the actual sun. You will burn a hole through the sensor, but in theory, that's what you would do, right? In practice, you would basically like set it like something really far away, like a mountain or a tree on a mountain, and you would try to do this, and that will give you the focal length of the lens. So this brings me neatly to this concept called field of view. As you start increasing the focal length, you decrease the field of view, which means that you are actually capturing a smaller area in the real world, but you are covering that with a larger sensor. You can sort of think of this as magnification. The bigger the focal length, the more zoomed in and more magnified something will look on your image sensor, right? And we go from something like a 180-degree fisheye lens, wherein you can see from the side of your ears all the way up to something zoomed in like this 400 millimeter or 800 millimeter or 600 millimeter focal length lens. This is the equivalent of an eagle being able to spot a rabbit from up to 4 miles away, right? And they have nice little terms. And as we go from the fisheye lens to the zoom lens, it's going to be called wide angle lens, then normal lens, then a telephoto lens, and then a super telephoto lens. Depending on what you're trying to do with this stuff, you're going to pick the right amount of things. An extreme wide angle lens might be important for you to capture a large part of the scene, like architecture or interiors. A wide angle lens is nice for like landscapes. A normal shot is good for like average, like how we would see it, and the human eye is closer to 50 millimeters in focal length. And a telephoto lens could be useful for wildlife or sports, and a super telephoto lens could be super useful for like birds, or like maybe like capturing photos of drones or like aircrafts and things like that. And I'm going to show you a simple example of how the same scene would look with different kinds of focal lengths. On the top left, 16 millimeters is a very wide angle lens, and as we keep going top to right and bottom, you will see that we are zooming in more and more, and you will see that at 200 millimeters you see the tower, which is super big, and in 16 millimeters it's barely visible, right? And if you're wondering where that the tower is right here. Okay, and remember in the previous few slides I said that there is a thing called an aperture, but I never really talked about what that is. Let's talk about that next. So just like our eye pupil, whenever something is too bright, we basically reduce the amount of light by closing in our pupil. An aperture is the exact same thing called a pupil of the camera. So the idea is that you have, as you go from left to right, you see f1.8 to an f11 lens. And you will see that like f1.8 is called wide open, which is almost letting in all the light. As you go from left to right, you will see that the amount of light reduces. You might be wondering, why would you want to reduce the amount of light? Do I not always want to have the maximum amount of light? The answer is no, because if you ever like look at the sun, you get blinded by the sun because there is just too much light and your pupil becomes small. It's the same exact idea for a camera, right? And this is specified, the aperture is specified in a camera as f-stops or f-number. And the f here basically means that it's the focal length, right? We say f1.8, that means the diameter of this opening pupil is the focal length divided by 1.8. So smaller the number, the bigger the aperture because it's in the denominator, but it's read as f1.8, not f divided by 1.8. Cool. And bigger the aperture, smaller the number, like we just said. And it's the ratio of the focal length to the diameter of the entrance pupil, which is the actual physical size. As you try to buy newer and newer smartphones, they will actually start reducing this f number so that you can let in more light, which means that your lower light performance of that camera sensor goes up and up and up, and that's why they get you better night shots in the newer cameras. So another like sort of little tidbit which I want you to remember is that increasing a stop of light is basically doubling the amount of light, and decreasing the stop of light is basically like reducing the light by half. So it's in powers of 2. So if you go from f2.8 to f4, that basically is one stop of light difference. So going from f2.8 to f4 reduces the amount of light by half, and going from f4 to f2.8 doubles the amount of light. Awesome. So another sort of artifact of why you want to use like a bigger aperture versus a smaller aperture is more artistic, but we can actually use some cool tricks to use that in robotics. So this concept is called depth of field. As you would see on the top left, the shutter speed or the time the shutter is open is shown on the number on the left, like 1/640th of a second, and you'll see the aperture on the right side where it says at f3.5. As you observe, as we go from top left to bottom right, your aperture is getting smaller and smaller as indicated by the increasing number on the denominator, but your shutter speed is compensating for that by dropping in time. So you might be thinking, why would I want to have a high shutter speed? If you're trying to shoot like a really fast object like a car or a rocket or a airplane or a drone, you would really need like a high shutter speed here. Right? As an artifact of that, what would happen is your aperture has to be physically big. So because when your aperture is big, you see that like in this case, we were focused on the front leaf. What happens is the background goes completely out of focus. Anything that is really far away from the distance of that like leaf where it is in focus, which is called the plane of focus, the farther away you go in either direction towards the camera or away from the object, it is going to get out of focus. As we get smaller and smaller apertures, the amount of out of focus will start reducing. This term is, or like this deliberate out of focus is also called as bokeh in photography, which is actually artistically used in portraits to make the subject stand out, which is amazing for photography, but not always great for robotics because you do want to see what is actually through and through the scene. So when you set a very small aperture, you can essentially get almost everything in the world in focus. To get this like bokeh, which is like this heart little shape, your aperture instead of being circular was actually a heart shape, as you see in this image. So this is a cool trick for you to get any amount of like defocus shape for a point light source like you see in the bokeh love thing on the top. And you can use this creatively and artistically for doing really cool stuff. But can we actually use this thing for robotics to do something cool? Let's ask a very simple question. does this depth of field give depth? Because remember I told you that like depending on where you focus, you set focus at let's say a meter away or 2 meters away. The farther you get away from that meter, the more defocused it will be. So in theory, like we should be able to recover depth given that something is out of focus, right? Let's have a look at a specific example here. Let's look at two different parts of the image. Look at the part of the image on the leaf which is sharp, the red part, and look at the part which is on the background which is much farther away. It's completely blurred out, right? So in theory, if we know the amount of defocus, we can actually backtrack depth from it. The problem is that when we do this in a circular pattern, it's too symmetric for us to be able to get depth very well. When we do this in a computational algorithm, it's actually not very robust, as we will see in the later few videos. So the question is, how can we do this better? Remember I told you that the problem is symmetry. So what we can do instead is we can take this aperture. Remember that we made it into a heart shape. We can technically make it whatever shape we want. We might not get pretty looking images out of it, but we can definitely use it to do some computation to actually backtrack depth. For a robotics application, it really doesn't matter how the image looks like to a human being, but it's more like, is it useful for the robot to do whatever task it needs to get done, right? So this is one particular example of making an aperture which is as asymmetric as possible. If you squint really hard, this might look like a QR code to you, and you would not be wrong in thinking that way, because it's the same exact idea as a QR code, which is making the pattern unique and robust enough that we can use it for different kind of application. In computer vision or robotics, this is called a fiducial marker, and this is an example of an April tag. And QR codes are just special cases of these kind of things. And this exact concept is called coded aperture, wherein you change the aperture with something which is asymmetric, and you can use a computational algorithm to actually recover the sharp image, and you can also recover depth from that. If you look at the image on the left, the image is a blurry mess. It doesn't look good at all, and you definitely cannot read any of the text, right? You cannot read the numbers. But because we know exactly how this aperture is made, because we physically made it, we can use a little bit of clever math, as we will see in one of the later videos, to actually backtrack and recover the original sharp image if this was a normal aperture, right? And you will see that image on the right, and you can clearly see the numbers really well. You can read the numbers on the car, you can read the pharmacy sign and so on. We use this very simple concept wherein we said, hey, we know that if we put a large aperture lens and open it up all the way, and we focus on some distance, let's say 1 meter, the farther away you go from 1 meter, the more defocus there is going to be. And the moment there is something that comes in focus at 1 meter, we just have to dodge it, right? And we basically put this on a drone, and then we saw that, hey, like, can we just use this simple concept for dodging? And this is a paper in WACV 2025, which was published with my students Rishikesh and Deepak. And they have done a spectacular job in demonstrating that this actually really works in the real world. And this is behind the WPI campus, and you'll see a video as I play next, which is basically the drone flying around. And as it gets close to the tree, I want you to observe that the sharpness image on the right, on the bottom, the black and white thing, the white is going to be the sharp part. You're going to see that the tree will actually be, all the parts of the image which will come to focus are going to be white. And the left thing is called an event image. Again, we will talk about what these cameras are. They're not like your regular classical RGB camera, and we will see that this is a cool sensor, which in the later parts of the episodes. Now, as we get closer, you will see that it gets very close to the tree, and the tree becomes sharp, and we actually can dodge the tree itself, right? And it's a really cool concept. We will cover this paper in more detail in one of the later videos, but I just want you to understand that you can go back to the drawing board and think of a very fundamental concept and utilize that in robotics today. And it's a very cool concept. Now, let's ask a couple of questions and see where we go from there. Imagine you have a really, really long zoom lens, which means that you can zoom in really far away, like the eagle vision, and you can actually see like really far away and really good details. But it has an extremely large aperture like f2.8, right? Which means that it can let in a lot of light. What happens when you have a lens like this? The question is, can you even make a lens like this? If so, why do we not see that commonly? The answer is, a lens like that would be extremely big and extremely heavy to carry, right? The Sigma lens is extremely expensive. It's about $30,000 to make one. Again, lenses get abnormally large. And for example, here I'm showing you a simple 600mm f11 lens, which weighs about 930 grams, versus a 600mm f4 lens, which is like almost like more than 3 kilograms, right? It's like 3 times larger just to have like that extra stops of light. And here is a more wild comparison of going from a 300mm f2.8 lens to an 800mm f5.6 lens, which is like almost like 3 times or 4 times the size, right? And it's just amazing how lenses can be this big. Let's take this to the extreme. This is like a very large lens, which we have, as humans, have put into the space. I just want you to take a second and think what this is. This is the Hubble Space Telescope. And can you guess what the focal length of the Hubble Space Telescope is? Remember, we were seeing about like 600mm and stuff in the back. Of course, the Hubble Space Telescope is a lot more than that. But the question is, how much more? The Hubble Space Telescope has about 57 meters of focal length. Let that sink in. We were talking about 600mm in the previous slide. This is 57 meters. It's orders of magnitude higher. Next, we also talked about there is a thing called the shutter mechanism behind, just before the sensor, right? We said, hey, the mirror flips up, but I never really explained how the pixels are actually captured. Remember that we have like millions of pixels in today's cameras, like your smartphone probably has 108 megapixels. The question is, how do you actually capture light in each of those pixels and actually read it out, right? That's what we are trying to ask here. The most common method is called the rolling shutter, which is what you see on the left side, wherein all the black pixels are basically what is being read. You'll see that each row is individually being read. It can be either done row-wise, it can be done column-wise, or it can be done in a raster scan, going from left to right and then top to bottom. This is in general very cheap to construct because you only need like a few readout values at the same time and you capture that. And we'll see what the problem is with that is in a second. The awesome thing is it's cheap, right? Then the other side of the world, there are cameras called global shutter cameras, wherein all the pixels are captured in one shot, boom. And that obviously is much better, but it's exponentially more expensive because you have a lot more digital readouts that have to be done at the same time. Awesome. Let's look at a small example of rolling versus global shutter. On the top, you see that it's a global shutter camera. On the bottom, you see that it's a rolling shutter camera. This is a snapshot from a helicopter like landing. You'll see that the blades are pretty much straight in the global shutter because there's no artifacting because of timing mismatch. On the bottom, because rolling shutter takes a finite amount of time to go from the top pixel to the bottom pixel. The top pixel arrives a little bit earlier than the bottom pixel, which makes you feel like this helicopter blade is curved in some sense. Remember, the helicopter blades are pretty much straight, but it looks like that. And I'll play also a video just to show you how this would look like. And you can clearly see the artifacts on the bottom which don't exist on the top. And look at the blades on the back. More than the top, it's easier to see that. It almost seems like the helicopter blades were rotating at a completely different speed and suddenly jumping and teleporting on the rolling shutter camera, which is definitely not true. But on the global shutter camera, you see that clearly that this is the right way to do it. Depending on the application you want, you might want to use a global shutter camera, especially for moving targets, and it becomes super important. If you don't really have that many moving targets and you really just want to save money, you can just use a rolling shutter camera. And again, most modern day DSLRs still use rolling shutter cameras. There are a few cameras today which use global shutter and their video quality is far superior because of what we just saw. Next thing is, remember that we talked about the image being captured as number of photons per unit time. The unit time is basically determined by what we call the shutter speed or the shutter time. This is the amount of time you let the sensor capture data, and this helps you get more or less data with more photons per unit time, more photons in that unit time. But the problem is that depending on what is happening in the scene, you might also see something called as motion blur. Going from left image to the right image, the shutter speed is going up or shutter time is going down. You'll see that on the left side, the basketball is a big blurry mess. As you go to the right, the basketball is pretty much sharp. The shorter you make the shutter time, the sharper your image gets. And if you keep everything else the same, it will also actually get like darker and darker. In this case, we have neutralized and equalized the brightness levels so that you see the same thing. Okay. So to adjust the brightness or the darkness of the image, one of the easiest thing is called the ISO. ISO comes classically from film photography, which is the analog film was basically exposed to the world light, and it would react with the molecules on the film and it would get exposed to get a negative. And depending on how dark the scene you wanted to shoot, you can buy film which has different amount of concentrations of the chemicals in them, and it would be exposed to light in a much easier way, right? And this is called concentration. And to mimic that concept in photography, we have something called the ISO or the film speed. Film speed is essentially the digital gain of the amplifier. It's like the volume knob on your amplifier on your laptop or the phone you're watching on. You can crank up the volume way up, but you'll see that there is a tiny bit of noise which will get amplified at the end. It's the same exact thing that happens with ISO being increased. ISO 100 is generally called the base ISO, which is the lowest ISO a camera can go. In today's modern cameras, you can go up to 64 or 32 even. And you'll see that in this image, like ISO 12800 is called a high ISO or an extended range, wherein the gain is bumped up like this extra volume boost. And you'll see a lot of graininess in the image, which is like color noise in the image, right? So bumping up the gain will let you have a lower shutter time, which might be required for you to capture something fast moving, like the basketball or that car or that bird. But again, remember that you will actually get a lot of noise. Later on in the classes, in the videos, we will also see how to reduce this noise using classical methods and deep learning. But remember that classically, you will actually get more noise when you bump up the ISO. The smaller the ISO, the better your image will look, but the longer your shutter time has to be. That's what I wanted to remember. To sort of like remember or like really realize what affects the brightness of the image or quote unquote like the look of the image, let's look at this cool thing called the exposure triangle. The exposure triangle basically tells you these are the parameters you can change in the camera and what actually it affects. Let's start looking on the left hand side here. You look at the aperture. As we go from a large opening aperture like f1.4 to something really small like f332, you'll see that like we let in lesser and lesser light, but we increase the depth of field, which means that wherever you focus, the farther away you go from that, there will be more things in focus the smaller this aperture gets, which is kind of cool. If you want a bokeh effect, you basically go for a high aperture, but the problem is that you cannot shoot in really bright sunlight because the image will become completely white. Okay. And on the other hand, you have this thing called the ISO or the digital gain of the amplifier. As you go down in ISO or go up in ISO, you'll start seeing basically more and more light with more ISO. You will also see more green with more ISO, like we just discussed. And the shutter speed is basically the amount of time the shutter is open for. And as you go smaller and smaller amount of time for the shutter is open, you will get lesser and lesser amount of light, but you will freeze the action much better with this stuff, right? And combining these aperture, ISO and shutter speed, you can get the look and feel of whatever you want. Whenever you set your camera to complete automatic, it sets all these three values depending upon the scene. If you set it in aperture priority, you set the aperture, ISO and shutter speed are automatic. If you set it in shutter priority, you set the shutter speed and aperture and ISO are automatic. And that's the idea. When you set it in full manual mode, you set aperture, ISO and shutter speed the way you want for the look you want. So the question is now, in all these scenarios, we never talked about how physically big the sensor is, right? This is the equivalent of me asking the question, does the human being see the same thing as the elephant, as the hawk, as the hummingbird and so on? The answer is definitely not the case, right? The sensor size does affect the way things are seen. And this is a simple example of that. What you see on the red periphery outside is called the full frame camera. A full frame camera is basically what is the physical size of an analog film, what we would shoot in the earlier days and made into a digital sensor. An APS-C camera, the blue one, is basically a smaller version of the same thing, which is what you will find a lot of these new mirrorless cameras or DSLRs which are cheaper. They're called the APS-C size sensors, or it's APS-C stands for a postage stamp, which means that the physical sensor is the size of a postage stamp in the US. And Micro Four Thirds is even smaller, the yellow one. Your iPhone or the smartphone camera is much smaller in that green box there, right? Compare the size of the green box to the red box. Of course, the visual quality of the cameras are not going to be the same, even if they had the same optics, just because the sensor is just much better, right? And we have this cool thing called the crop factor of the camera, which is basically if you take any sensor and normalize it to a 35mm camera, it's how much are you going to crop in to get that size. So anything which is a smaller sensor has a crop factor greater than 1. Anything which is bigger than this red sensor will have a crop factor less than 1, which means that you have to crop out or the sensor is physically bigger, right? And there is this example called a medium format camera, which is almost double the size of a full frame camera, like we saw before, and that has a crop factor of 0.5. And you'll see that like our smartphone cameras, which use something like 1/2.3 inch sensors, have a crop factor of 5.62, which is very impressive, right? Which means that it's very, very small compared to this camera, like the full camera we are using. And again, as we were talking, the sensor size does matter. Like depending on the sensor size, you can get varied amount of different outputs. And I just wanted to take a second and ponder upon why sensor size matters. And if it does matter, what am I keeping constant for it to actually matter? So one of the things that can happen is if you keep the amount of the pixel size the same in physical units, then you can have basically more pixels if you have a bigger size sensor. If you keep the number of output pixels the same, then you will have bigger physical pixels, which means that you have more light entering the sensor and each pixel. So you will actually have a much better noise performance when you crank that ISO up for a dark night sky photography, right? But not always bigger sensors are better, because bigger sensors mean that lenses have to be larger, and then the sensors physically are more expensive to construct because they use more material. Let's play a small game and let's pick a lens and a camera combination for what you want to do, right? Let's say you were designing a robot for dodging dynamic obstacles. What kind of a lens and a camera would you use? We would be using a bigger sensor because we want to capture with shorter shutter speed, and if we bump up the ISO up, we want physically bigger pixels for it to work well. And we would basically use either a wide or a zoom lens depending on the kind of scenario we want. But the only thing we are 100% sure of is that we want a lens which has a big wide aperture so that we can actually have the shutter time to be really small. So what about low light photography? It's exactly the same thing. We would want a lens which is wide open, preferably something wide, because low light photography with wide for shooting astroscapes is nice. And we definitely want a physically bigger sensor like we just talked about. So dodging dynamic obstacles and low light photography are actually very similar in spirit, right? And just for understanding here, I want you to understand why the camera is an ubiquitous sensor, and how does imaging sensors work, what are the components of the exposure triangle, and why does sensor size even matter, or if it does not matter at all. Thank you, and see you next time.